Good morning. I welcome you all to this session of fluid mechanics. So, today we will be discussing the introduction to turbulent flow, which we have started in the last class. Now, we were discussing about the modification of Navier-Stokes equations with the use of the velocity component in a turbulent flow, which can be prescribed as a mean component plus superimposed with a fluctuating component as suggested by Reynolds. We discussed last class. So, let us today continue that how the Navier-Stokes equation is modified in case of turbulent flow using this Reynolds decomposition principle to specify the velocity components in a turbulent flow. So, before that we will see that Navier-Stokes equation for such purpose is written in a little different form from the conventional one which we discussed in the previous chapters like laminar viscous flow theory. So, let us see that the Navier-Stokes equation, if you consider the x direction Navier-Stokes equations for an incompressible flow x direction, that means if you consider this x coordinate, y and z, if we take only the Cartesian x coordinate. So, Navier-Stokes equation for an incompressible flow is like that, rho u del x. That means this is the left hand side, as you know, is the inertia force per unit volume, that is the acceleration per unit acceleration times rho u del x plus v del u del y. As you know previously, u, v, w are the velocity component in x, y and z direction, w del u del z is equal to the pressure force, that means minus del p del x per unit volume, plus the viscous force mu del square u del x square plus del square u del y square plus del square u del z square, and the other term is 0, another term is there because of compressibility of the fluid, but for incompressible flow this is 0. Now, this left hand part is written in a little different form for such a purpose modifying these equations in turbulent flow. How it is done? Now, if we recall the Navier-Stokes, the continuity equation for an incompressible flow, that is with respect to a Cartesian coordinate system, this looks like this. Well, now if we multiply this equation with rho u throughout, then we can write the continuity equation like this, multiplying the basic continuity equation with rho u. And then if we add this quantity in the left hand side, which is equal to 0, that means this quantity we add left hand side, that means with this we add this quantity, that is rho u, because this quantity is 0. So, we can add 0 to the left hand side without altering the equations. So, plus 0, which is equal to this quantity. Then we can see one thing, that if we take rho as common, then u del x plus u del x means 2u del x, which can be written as del x of u square. So, make it a second bracket, plus you see this v del y plus u del v del y, this term makes it del y of u v. Similarly, if we add up this term u del w del z and w del u del z, it gives the terms del z of u w. Okay? And the right hand side remains as it is, minus del p del x plus mu this quantity. This term can be written by taking rho inside, because rho is a constant, it can go within the operator. So, del x of rho u square plus del y of rho u v plus del z of rho u w. Now, I write again the right hand side to make this equation complete, that means the same quantity. Let me write mu del square u del x square plus del square u del y square plus del square u del z square. Now, this is the form in which the Navier-Stokes equation is written in a slightly different form. So, for a compressible flow also, if we use the equation of continuity for compressible flow, which is del x of rho u plus del y of rho v plus del z of rho w, and you manipulate it by multiplying u with this is equal to 0 and adding it. So, you will get the same term in the left hand side. Difference is that for incompressible flow rho is constant, it can come out. Whether for a compressible flow it cannot come out from these differentials. And another thing is the right hand side will contain another term for the compressible flow. So therefore, this is one form of the Navier-Stokes equations. Now similar way, if we think of the y direction equations, u del v del x plus v del v del y plus w del v del z is equal to minus del p del y plus mu times the Laplacian of the velocity component in the y direction, that is del v square del x square del square v del y square del square v del z square, can be written also in a similar fashion like that by multiplying rho v with the continuity equation and adding it in the left hand side. And this way if we do for all the three directions Navier-Stokes equations, ultimately we will come to this type of form of equations, that is x direction, this is the form we have already derived, y direction the form will be like this, and z direction only the left hand sides will be written in a different fashion with the manipulation with continuity equations. So this term clearly indicates the momentum efflux. For example, this is the x momentum efflux across a plane whose normal is in the x direction. We call that plane as x plane. Similarly, this is the y momentum efflux across x plane. This is the z momentum efflux across x plane. Similarly, this is the y momentum efflux across y plane. It is the x momentum efflux, y momentum efflux across y plane. That is a plane whose perpendicular is in the y direction, and z momentum efflux across y plane. So therefore, these terms, instead of defining the acceleration in the previous form of equation, defines the momentum efflux. So this form of Navier-Stokes equations is known as conservative form. So writing Navier-Stokes equation in this form in any coordinate system is known as conservative form. Now we come, after that, we come to modify this Navier-Stokes equation, this form of this Navier-Stokes equation. So before modifying these equations for turbulent flow, we recall the turbulent flow specification. We know that u is specified by some time mean value plus fluctuating component, v is time mean value, this we have recognized in our earlier lecture, where we know that u dash is 0. Obviously by this definition it is, that means the fluctuating component is such that their time mean value is 0. But there are certain algebraic rules for this. What is this? Let us find out u square, that means square this quantity. So this will be the square of this, that means this square plus twice u bar u dash plus u dash square. Now if we average the square of u, that means time mean value of the square of u, so what we get? We have to average this entire term, that means each and average of all these three terms means sum of the averages of these three terms. So separately average plus average of the second term, time mean value. Average means time average value, time mean value. Now this u bar square is the time mean value which is independent of time. So again if you make an time mean value, that means it is a constant, so it is like this. Similarly here u bar is the time mean value which is independent of time, so it can come out of this bar, that is the time mean, this becomes like this, u dash square average. Now as per definition this is 0, so the middle term becomes 0. So therefore we get a very important conclusion like this, plus u dash square. We know that this is 0, but u dash square average is not 0. Similarly v dash square average is not 0. So time mean value of the square of the fluctuating components are not 0. In the similar way, we get that v square average is square of the average v plus v dash square. In the similar way, we get w square average is w average square plus w dash square average. That means the average value of the square of any velocity component is equal to the square of the average value of the velocity component plus average value of the square of the fluctuating component. This is the representation of turbulent intensity as we have already discussed earlier. Now we see another rule for product of the term. Now if we multiply any two velocity components, let us multiply u and v, u and v, what do we get? U bar v bar plus u bar v dash plus v bar u dash plus u dash v dash bar. u dash v dash. So therefore, if we make a mean of uv, then we get mean of this quantity plus second quantity mean plus third quantity mean, that means mean of the third quantity plus u dash v dash, fourth quantity. Now you see therefore what happens. The mean of this, these are all time independent, so this becomes like this. So this can come out, that means u bar v dash mean plus this will be v bar u dash mean plus u dash v dash. So v dash mean is 0, mean of the fluctuating component, u dash mean is 0. So therefore uv mean is equal to this quantity. And we know from the definition of turbulent flow, though u dash mean and v dash mean is 0, but the product of the mean and their average is not is equal to 0. So therefore we get a rule that the mean of the product of two velocity component is equal to the product of their mean values plus the mean of the product of their fluctuating component, and this is true for other velocity component also. So this is u dash w dash mean, and similarly v w mean is v mean plus v dash w dash mean. So with this rule, now we can modify the Navier-Stokes equations which have been written in conservative forms. Now how we do it, let us see now. So therefore we have arrived as such rules for the squaring and taking the mean for the velocity components and their product and the mean. And another rule that, for example, if you take the mean of a differential, it is obvious from the basic definition of this mean value, it is a time average value, a simple algebra, it can be written as the differential of the mean. So with all these rules, now let us look how you do the modifications for the Navier-Stokes equation. Let us see the x direction Navier-Stokes equation in the conservative form, which we have just derived. And the first step is that we take the time average quantities of this Navier-Stokes equation. That means physically we try to express the equation of motion on a time average basis. That means we make the time average for both the left hand and right hand side. So term by term we take the time average value. Now left hand side you see this time average value del x of rho u square, by using this rule will be del x of rho u square average. Now rho is the incompressible fluid, so we are not considering its fluctuations. So it is out of the turbulent quantity, so it will be only u square average. Similarly, the average of this differential of any parameter, fluctuating parameter, is the differential of their average. That means del y of rho u v average plus del z of rho u w average is equal to, similarly by this rule, minus del p. P is also a fluctuating quantity in a turbulent flow, plus mu. Similarly, each and every quantity, the average of the sum of the three quantities is the sum of the average of the three quantities. And again, the sum of the average of this differential operator is the differential operator of the average quantity. That means del square u average del x square plus del square u average del y square plus del square u average del z square. So right hand side becomes simple. But in the left hand side, now we express u square average, uv average by this, u square average by this equation, and uw average by this. Then what we get? So if you replace this, we get del x of rho u bar square. So another term we get del x of rho u dash square average. So fluctuating component now I am taking on the right hand side. So keeping only this component, the mean component in this side, del y, a little algebraic manipulation will tell you. So here also del y of rho u b average means u average b average, u bar v bar, plus u dash v dash bar, which we will be taking separately on the right hand side. This term is here we will take it in the right hand side, plus del z of rho u is equal to minus del x, the same quantity in the right hand side as usual, del square u bar del x square plus del square u bar del y square plus del square u bar del z square minus the quantity which comes from here. Here del x of u dash square average bar, that means minus, if we take del x of rho u dash square average. Similarly, from here we get del y of this quantity rho u dash v dash average, well, minus del z of, that means from here rho u dash. This is very important. That means we see here, after using these rules, and then what we have done, again I repeat, by making the time average of each and every term in the left hand and right hand side of the Navier-Stokes equations, we ultimately see that the time mean value of the Navier-Stokes equation is same in the left hand side if we replace the velocity components by their mean values for the right hand side also, plus some added terms. These three terms are the added terms. These three terms, this we take for some purpose that will be explained afterwards in the right hand side. So, apart from these three added terms, the equation remains the same. That means, if we compare up to these equations with the equation without taking the time average, they are same. Only the velocity components are replaced by their time average values plus some added quantities or added three terms, which are the terms containing the fluctuating average values of the fluctuating component. So, if this way we perform the modifications for three equations in three directions, we get this thing. This we have derived earlier. So, del square u bar we have written in short for the want of space, that is the Laplacian u bar, that is del u bar square del x square plus del u bar square del y square plus del u bar square del z square. Similarly, in y direction, the equation, the left hand side equation in the conservative form, which was earlier done, this is the conservative form of the y direction equation, if you recall this equation. So, similarly, if we replace it by the bar quantities, then the additional term, these three terms, these additional terms come. So, for z direction equation also, it is the same equation in the conservative form with the velocity components, which is replaced by their mean values, average values, but extra three terms come of this sort. So, these extra terms come in the modification of the Navier-Stokes equation, that is the time mean value of the Navier-Stokes equation. Now, we want to see the physical implications of this term. Let us see the physical implication of this term. Now, if you consider what are the terms we have got, now you see the physical implication is like that. What is the physical implication of rho u dash square average, rho v dash square average, rho u dash v dash average, rho u dash w dash average? These are the terms which have appeared with differential notations, rho v dash w dash average. What they physically signify? Let us see, consider a plane, x plane, whose normal is in the x direction. Let us consider some x direction here. So, therefore, you see, if u dash is the fluctuating component of velocity in x direction at any instant of time, therefore, rho u dash is the mass flux across the section here. If we consider Ax is the cross sectional area of this plane times Ax, this carries an x momentum, which is this one. So, rho u dash square Ax is the x momentum at any instant due to fluctuating component, x momentum a flux across a cross section whose perpendicular is in the direction of x. So, therefore, rho u dash square average represents the average x momentum a flux per unit area, because Ax is being cancelled. So, therefore, this quantity represents the average x momentum a flux across this section, okay, that means across x area, x plane, that whose perpendicular, whose normal is in the x direction. So, this is experienced as a stress, normal stress. As you know, the momentum efflux in one direction across a section can be conceived by a stress. So, stress will be in the same direction in which the momentum efflux is taking place. That means it constitutes a sigma x. We give sigma x dash to discriminate it from the laminar stress sigma x, which arises due to molecular momentum transport, because the stresses at any plane is responsible for the momentum transport across that plane. Because of the molecular momentum transport, the laminar stresses arise, which we have already discussed earlier in the beginning of this course. So, similarly here, because of the momentum transport associated with the fluctuating components, that means the momentum transport by the macroscopic mass of fluid, some additional stresses are coming. Now, let us see what is rho v dash square. Rho v dash square in the similar way, if we consider a y plane, that means whose perpendicular is or normal is in the y direction, this is y direction. So, rho v dash square average in the similar fashion shows the y momentum efflux across this y plane, which is conceived in terms of sigma y, a normal stress in the y plane, sigma y dash. Similarly, if we consider a z plane, that means this is the z direction. So, here also the quantity rho w dash square, it represents the z average efflux of the z momentum across the per unit area, of course, across the z plane. This area is AZ, and that is conceived in terms of a normal stress sigma z dash. What is rho u dash v dash? Rho u dash v dash can be conceived for this x plane as the y momentum, average y momentum efflux across x plane, because the mass flow is rho u dash x with the y component of velocity per unit area cancels the average. That means average y momentum efflux across x plane, which can be conceived as a stress in the y direction in the x plane, which is the shear stress tau yx. Similarly, this quantity can be conceived as an average x momentum efflux across the y plane, so that this can be conceived as a x direction stress in the y plane, that is tau yx, a shear stress. Similar way, rho u dash w dash can be considered as an average z momentum efflux across x plane, and can be considered a stress in the z direction in the x plane, that means a shear stress tau zx. Similarly, rho u dash w dash can be considered as an x momentum efflux across z plane, and which can be considered as a shear stress in the z plane in the x direction tau, that can be tau zx, and it is tau xz, rather z direction xz, tau zx. Similarly, rho v dash w dash, this can be expressed as a y momentum efflux across the z plane, and can be considered as a y direction stress in the z plane, tau zy. And similarly, this can be seen as a z momentum efflux across y plane. So, this can be expressed as a z direction force, that means shear stress in the y plane, that is tau yz. So, therefore, now we can sum up with this, that sigma x dash, then additional stresses are developed because of this molecular momentum transport. Because of the molecular momentum transport associated with the fluctuating component, these are like this. Rho, this is the average x sigma x direction normal stress, sigma y dash is rho v dash square bar, and sigma z dash is rho w dash square bar. And we have seen that tau xy or tau yx, this is also symmetrical, is rho u dash v dash bar. Similarly, tau yz is equal to tau zy is equal to rho v dash w dash bar, and tau zx is equal to tau xz is equal to rho u dash w dash bar. So, you see that again 6 distinct stress components are coming additional with the laminar stress components. So, we can write this as a different stress matrix or stress tensor like that, sigma x dash, tau y x dash, tau, this is in x direction. So, therefore, tau z x dash, so tau x y dash, they are symmetric, sigma y dash, so tau, this will be x y direction, tau z y dash, similarly tau x z dash, tau y z dash, and sigma z dash. So, these 6 additional stress terms, which are equal to minus of, if we take rho common for an incompressible fluid, u dash square average, u dash v dash bar, and u dash w dash bar. Similarly, this will be u dash v dash bar. These are symmetric. So, therefore, v dash square bar. So, v dash w dash v dash w dash bar. Here we get u dash w dash bar, these are symmetric, then it will be v dash w dash bar, and then w dash square. These are the normal stress diagonal element. So, this is the additional stress is developed, and this is known as Reynolds stress according to the name of the scientist who first derived it, or turbulent stress. This is an additional stress coming along with the normal stresses in the due to along with the stresses in the laminar flow. So, therefore, now if we look, we can see that these equations here, this can be written as sigma x dash, tau x z dash. Similarly, tau, it is same, xy dash sigma y dash tau yz dash. Similarly, we can write I xz dash tau yz dash sigma z dash. That means del del x of sigma x dash del del y of tau xy dash del del z of tau xz dash. If we recall, then we see that this quantity also can be replaced by del del x of sigma x plus del del y of tau xy plus del del z of tau xz, which are the stresses for the laminar flow, which if you recall we first started with this when we derived the Navier-Stokes equation. So, if we recall this term to be written in terms of the laminar stresses, similarly for y direction and z direction, we can write this way. For example, the x direction equation, that means minus del p del x plus mu del square u bar can be written like this. That means because of the molecular momentum transport, the laminar stresses. So, this is the net surface force in per unit volume in the x direction. Similarly, this is the net surface force per unit volume in the x. That means an additional surface forces occurs in case of turbulent flow. So, these two can be added together. That means you see always an additional shear stresses are coming because of the turbulent flow. Now, if you recall the definition of sigma x in laminar flow, it was minus p plus 2 mu del u del x. Similarly, tau ix is mu del v del x plus del u, well it is the shear rate in xy plane, it is the shear rate in zx plane, and whereas these additional stresses we have already recognized this thing. So, therefore, the net stress sigma x is can be written as for example, this laminar part. Now, we give it this as the laminar part and this as the turbulent part. So, laminar part plus turbulent part. Similarly, tau xy or yx whatever you call is equal to laminar part plus the turbulent part. Turbulent part is the dash quantity and laminar part is this quantity, which is the laminar part stress is related to laminar viscosity mu in this fashion, mu del b del x plus del u del y twice mu del u del x, whereas the turbulent stresses are related to the fluctuating component of velocity. Now, you see the most interesting task in this contest comes that how do you relate now these turbulent stresses in terms of the velocity gradient of the mean flow. This is because of the fact, if you now look back here, you see the most difficulty in integrating these equations to find the flow field is the occurrence of this fluctuating component. This is because the erratic behavior of the fluctuating components or its random fluctuations with time, we do not know an exact mathematical formula of this velocity component with time. So, it is very difficult to integrate this equation. So, if by some means we can relate these additional stresses through some parameter with the velocity gradient described by the mean flow velocities as it is done in case of laminar stresses, then we can integrate this equation, and that is the sole philosophy of a turbulence modeling, which relates the fluctuating components which creates the stresses. That means in one word, which relates the turbulence stresses with the gradient of the mean velocity through a parameter like the viscosity in case of a laminar flow, and then expresses the equations of motions, that in Navier-Stokes equations in a laminar form similar to the laminar regime equation, and integrate it. That is the sole purpose or the philosophy of a turbulence modeling. Now, I will discuss different turbulence modeling, different turbulence model. One is this Eddy viscosity model. One is the Eddy viscosity model. Now, if we take a very simple case of a one dimensional flow, for example, you take a boundary layer equation u del x. So, if you make a modifications with the time as the way we have done for the complete Navier-Stokes equation, what you will get? You will get, for example, minus del p del x, that may be with pressure gradient, does not matter, pressure gradient may be there depending upon the curvature of the body, mu del square u del y square, which means we can write this thing, this mu del square u del y square part, this part let it be like this. So, mu del square u del u square part we can write, so del y of plus rho u dash v dash, but sorry, this is the extra term for the del y, I am sorry, for the turbulent flow. So, mu del square u del y square can be written as laminar stress del y of tau L, which is mu del u del y, and ultimately this term comes, plus the additional terms del y of rho u dash v dash. So, therefore, you see the left hand side remains same, right hand side the pressure part is like this, it comes straight in terms of the mean pressure. But what is the difference? That along with the laminar stress, we come to a turbulent stress, tau t. How to relate that? In a simple case, I just explained how to relate that. So, it was Boussinesq first, Boussinesq is a great scientist, Boussinesq, who first proposed, why not we tau L is mu del u bar del y. So, similarly, we define a turbulent viscosity which relates tau t is equal to, it is a minus sign, I am sorry, minus rho u dash v dash bar, it will be a minus sign there. So, this will be del del y of minus this, I am sorry, minus this. So, that minus rho u dash v dash bar should be related with the mean velocity gradient through a similar term like laminar viscosity, a term mu t, which is known as turbulent viscosity. Why not we do it? Turbulent viscosity, or it is known as eddy viscosity. Eddy viscosity. But the difficulty comes that, well, we could have been happy just like the laminar flow equation, that we know laminar flow shear stress is linearly proportional with the shear rate. In such a simple flow, so del u del y is the shear rate. So, therefore, mu times del u del y, mu is a constant of proportional, which is a fluid property, which does not depend upon the flow field. If it could have happened for the turbulent flow also, the turbulent stress is proportional to the shear rate defined by the mean velocity gradient, we could have been the most happy man. So, that mu t becomes constant, is a property of the fluid. But unfortunately, even if you forcefully define the turbulent stress in terms of the velocity gradient with using the mean velocity, the mu t does not become the property of the fluid, or it does not remain as constant as it does in case of laminar flow. So, mu t depends upon the flow field. So, therefore, again the problem comes how to relate this mu t. So, therefore, we must have a relationship of mu t as a with the space coordinates in the flow field for integrating these equations. So, therefore, eddy viscosity gives a clue to solve this equation, provided more information is known about the turbulent viscosity or eddy viscosity. That means as a function of the space coordinate for this turbulent or eddy viscosity. Okay, so this is eddy viscosity model. So, one step further regarding this was given by Prandtl. So, we will now discuss his model, which is known as Prandtl mixing length theory. Now, Prandtl, the great scientist who gave the revolutionary concept of boundary layer theory. So, Prandtl mixing length theory. What Prandtl did, mixing length theory, he actually proposed a sort of mean free path in a turbulent flow. You know, the turbulent flow, the fluid particles move haphazardly in all directions and their velocity is randomly fluctuating with time. So, he had an intuition to think this as a similar phenomenon that happens at the molecular level. You know, the laminar stress is a consequence of the molecular momentum transport. Molecules are in continuous thermal agitation in any substance, in a fluid so. So, therefore, due to this random molecular motion, we get the laminar stresses because of the molecular momentum transport across the section. Similarly, he thought of that similar type of motions of the macroscopic fluid particles, which are random in both space and time coordinates. And then he thought in terms of a mean free path distance. That means, though there are a number of molecules in a system which are randomly moving in here and there, but still there is a finite, which may be very small but not zero, a statistical average distance before two successive collisions. Before two successive collisions, that means molecules travels a distance before two successive collisions. Similarly, he described that there must be a length that a fluid element travels before two successive collisions. That means it retains its original velocity and the momentum as it is for certain distance of its travel, and that distance is known as Prandtl mixing length, because after that distance it mixes with another particles. That is why the name mixing length comes. So, let us define the mixing length theory like that. Let us consider a velocity profile for a one dimensional flow. Let we define the velocity profile like this. Let we define a velocity profile like this. That means u bar is a function of y. Let us define. And let us define from any datum plane, let us define that is a flow past a surface where from we measure the coordinate. Now, let us choose a particular coordinate y1 at height, where we will pay our attention, and let us choose in an exaggerated way that the one layer at here which is at a distance y1 plus L, where L is such mixing length, and this is at y1 minus L, so that this distance is L, this distance is L, and we focus our attention at this level at y1. Now we see what? So because of this, now L is the mixing length where it was defined that a molecule retained its momentum, same momentum, retained its original momentum while traversing this distance L. Now we see, according to Prandtl, he told that at any section y1, the velocity component u has a fluctuating component u dash. The value existence of is u dash is due to the arrival of fluid particle from these two layers, one layer down to this layer, one other layer above this layer, below this layer, above this layer. Now let us consider that the fluid particles which comes from a layer L below this layer, which carries a velocity which is equal to existing at that layer, that means u bar, that means y1 minus L. Similarly, the fluid particles which comes from this above layer, a layer L above this layer at y1 carries a velocity to this layer, because they retain their velocity while traversing this length L1. So therefore, a change in velocity takes place here because of the arrival of a fluid particle from a layer L below that, can be written as delta u here, delta u, that absolute magnitude delta u, the average values of delta u at 1, delta u1 is what? u1 which is existing at y1 minus u bar y1 minus L. Similarly, the change in the velocity component, that absolute value, and take its average, because absolute value if you average it, it is not 0. So it will be u bar y1 plus L, because the velocity of the particle which arrives here from a layer above this layer, L height above this, will be this u y1 plus minus uy. So therefore we can tell the net change of this value is the mean of these two, that means mean of these two, that means half of this minus this, that means u bar, you can take a second bracket, y1 plus L minus u bar y1 minus L. So this is so, and he then argued that this causes the fluctuating component. That means if you express the mean value of the fluctuating component, because if you take the absolute value and then mean is non-zero, it is equal to this. And this can be written in terms of the gradient of this velocity field at this point as del u bar del y at y is equal to y1 times the L with a central difference scheme. So this can be written, the difference between these two, half of these two, between these two values can be written as this. Now with this and with some philosophy, we can express the turbulent stresses. Now how to express this? Now we have to understand one thing which was given by Prandtl, that this is because of the arrival of these two particles or many particles from this two layer to this existing layer, they collide each other and then again they separate and reverse their direction. So therefore the V dash component, that means the fluctuating component in the transverse direction, is originated because of the collisions of these two particles which arrive at this layer and makes the change in velocity like this. So with this philosophy he proposed that this V dash absolute bar, that means the mean value of the fluctuating component in y direction, is proportional to this, which means that V dash bar can be written as some constant into u dash bar. And moreover he argued that the statistical average of this, product of this, can be written as some constant C2 times the product of this. Now if we have these two in our mind, we can now write turbulent shear stress at this is equal to tau xy at turbulent shear stress is, what is that? Rho u dash v dash average. That means we can write C2 this one, and again this is proportional to that, so C1 C2 u dash square this square, which can be written as 1c, and this is equal to rho is of course there, rho c L square del u bar del y whole square. Now if we take this C into L, so that mixing length is defined taking this C punched into it or taking care of this C into it, that means rho L square. That means he defined the mixing length in this fashion. So he wanted only one constant will be there, that is the mixing length is equal to minus rho u dash beta. But here minus sign is there, that is taken care of in this fashion. I tell you that u dash v dash batch is proportional to a negative quantity of the product of this. This has to be understood. This is because this positive value of this to generate, there will be a negative sign because the u dash and v dash are in opposite sign. That means a positive value of v dash causes a negative value of u dash and vice versa. Let us verify it here. Now when the fluid particle is arriving from this layer, the v dash is positive, but when it reaches here, it reduces the velocity here. Delta u is 1 is negative actually. We have defined the absolute value, that is u bar y1 minus this, but the change in the velocity will be this minus this, because this fluid particle will retard this velocity at this particle because this is having a slow motion. And similarly when this particle arrives here, that means this is associated with the negative value of the v dash, that is the y component of velocity is negative. But when it comes here, it increases the velocity, that means influence on del u1, the change in the x component of velocity is positive because this particle accelerates the velocity at here. The similar way as the molecular momentum does in laminar flow. So therefore u dash and v dash are associated with the opposite signs. The positive value of v dash makes a negative contribution in u dash and vice versa. So that when we make this statement, we tell this is negative, the proportional to u dash and v dash, they are mean values, absolute values, mean of the absolute values with a negative sign. So that if you make this definition minus rho u dash v dash bar, you get a positive value. So this is precisely the Prandtl mixing length theory. So by the Prandtl mixing length theory, we see that tau xy in a simple case of one dimensional, that parallel flow is equal to minus rho u dash v dash bar is equal to rho L square del u bar. Now here also we are not very much satisfied. That means if we substitute it, for example, well, if you now substitute this here, so can you still integrate the equation? Why? Because if you substitute this in our equation, we get del y of, okay, mu del u bar del y for the laminar part, and for the turbulent part rho L square del u bar del y whole square. I understand, where L is the mixing length, sometimes known as Prandtl mixing length. But still there is a problem. What is the value of L? Is it constant, or what is this functional relationship with the space coordinates? So therefore a relation of that type is needed. Usually it has been found from experiment, this L is proportional to the distance from a solid wall that measured at any distance y from the solid wall as lambda into y, where lambda is known as von, he is a great scientist, German scientist in the field of fluid mechanics, von Karman constant, and its value is 0.4 approximately. So one interesting thing is that at y is equal to 0, at solid surface L is equal to 0, and there is no turbulence stress. It's so because at solid surface, exactly due to the no slip boundary condition, the velocity is 0. So therefore, and near the solid surface velocities are slowly reducing and drastically coming to 0 near the wall. So therefore you see whatever may be the turbulent fluctuating velocities, so all this kinetic energy will die out near the wall. So therefore near the wall turbulence cannot exist. So exactly at the wall the existence of turbulence is 0. So there is no turbulence stress. So under any turbulent flow conditions at the wall there will be no turbulent stress. So similarly at y is equal to 0, L is 0. This is satisfied by this equation. So if we take this value L is equal to lambda y and taking a constant value for this von Karman constant lambda is 0.4, then we can integrate the equations for a simple case. This is the Prandtl mixing length analogy. Now I like to discuss the velocity near wall region. Velocity in near wall region. Now the most important thing is that when there is a turbulent flow, just now I have discussed that near the wall, because of the viscous interactions, so turbulent flow is dying out. So therefore, if you study the turbulent boundary layer, you will see that whatever may be the turbulence level, degree of turbulence, turbulent intensity is very high, the fluctuating components are very high, so that their mean values are very high, but these are arrested near the wall. So very near to the wall, adjacent to the wall, turbulent flow is not there, there is the laminar flow. So therefore, there the turbulence law, turbulence velocity profile will not hold good. So let us discuss it through first a boundary layer, turbulent boundary layer. If we see the turbulent boundary layer, first we see the turbulent boundary layer. Now let us consider over a flat plate. The flow takes place. Now just after at the leading edge the flow doesn't become turbulent. After some length the flow becomes turbulent and the turbulent boundary layer grows. So here is the point where the turbulent boundary layer takes place. So turbulent boundary layer is also thinner, though it is more than the laminar boundary layer, but is very small compared to any characteristics length of the problem. But very near to the laminar, very near to the plate, so solid surface or the flat plate, the flow is like a laminar and it is known as laminar sublayer. It is known as where the flow is laminar. Now in fact, if you see the velocity distributions, you will see in the laminar sublayer velocity is almost linear, then it goes like this in the fully turbulent region. So this is the turbulent zone, this is the turbulent zone, and this is the laminar sublayer. In fact, very strictly we can define a section into three zones. One is laminar sublayer, which is very near to the solid surface, adjacent to the solid surface in the near vicinity, where viscous stress is much greater than the turbulent stress. So viscous stress is prominent, so it is purely a laminar flow. Another layer is the buffer layer. This, the name itself means that it joins two layer, buffer layer, that means just after after the laminar sublayer, where the viscous stress is almost in the same order of magnitude of turbulent stress. Well, and another one is the fully developed turbulent layer, or simply we can tell turbulent layer, where turbulent stress is very greater than laminar stress. So one can neglect the laminar stress in solving the equations in that zone. Usually the buffer zone and the turbulent layer can be mixed up to tell only the turbulent zone. Sometimes we tell there are two layers, one is turbulent zone or another is the laminar sublayer zone. Now we come to find out what is the velocity in the near wall region in the turbulent zone. So now to do this, if you consider a simple equation, for example the boundary layer equation, which can be written as rho u bar del x. For example, you consider a boundary layer equation, it will be easier for you, where we can show that the rest part, the second two parts, mu del square mu, for example, if I write del square u del y square plus rho u dash v dash bar, we can write this as del y of, this is the laminar stress, minus of rho u dash v dash bar. So del y, this term is del y of minus rho u dash v dash bar. So this is, we can write tau t, rho u dash v dash bar minus rho u dash v dash bar is the tau t. Okay. Now tau L plus tau t. Now if we consider very near to the wall, where the inertia force influence is almost 0, and if we consider a 0 pressure gradient at the same time, 0 pressure gradient. Now at this juncture, probably I must tell you one thing, that that probably while I have told you the stress tensor in the turbulent flow, just a minute, on negative sign, because all the time I am making this mistake, negative sign. Okay, I am sorry, that negative sign, I am correct, negative sign was taken at that time. I was scared that 0 pressure gradient, then what we can tell, that this is 0, that means del y of tau L plus tau t near the wall is very 0. Now if we consider the viscous layer or the laminar sublayer is very small, that it is only the tau t, then neglecting the laminar sublayer, considering it is very thin, we can take this 0 and tau t is. So therefore we arrive that tau t is, sorry, del del y of tau t is 0. That means shear stress is constant. Now with this we can now show that the turbulent shear stress is rho u dash v dash bar now is equal to constant. Now here we do one thing, we can find out this rho u dash v dash bar in other way. Now you see, if we define that tau w, now tau t is rho u dash v dash bar, so we can write that tau t is constant, that means throughout the turbulent zone near the wall, tau t is tau t at y0, where tau t y0 is the shear stress at the laminar wall, which can be also written as tau w. Considering the laminar wall is thin, so that the same shear stress is there totally in the laminar sublayer or viscous layer. Now defining a velocity equal to root over tau w by rho, which is known as the friction velocity. That means tau w is equal to rho v star square. We can write tau t is rho v star square by using the friction velocity v star. Now tau t is what? Tau t we can write in terms of the Prandtl mixing length theory, rho L square. Now using the Prandtl mixing length, we can write rho v star square. Okay, rho cancels. Now if you take square root on both sides, del u bar del y is equal to v star. All right. Now L is lambda y, so lambda y del u bar del y is equal to v star. So after this we can write del u bar is equal to v star by lambda. So this can be written as dy by y. Okay, or this is du bar, we can write du bar dy, because here u bar is a function of y only in one dimensional parallel flow. So therefore we can write u bar is v star by lambda ln y plus some constant, or u bar by v star is 1 by lambda, lambda is the von Karman coefficient, L is equal to lambda y, we have substituted here, plus c. This is a dimensionless velocity and is defined as u plus is 1 by lambda ln y plus c. So this is the law near the wall and known as logarithmic law. The constants are found from experiments. Let us find out the law in the laminar sublayer now. Now laminar sublayer, tau w is constant, so we can write tau w is mu del u bar del y. Laminar stress is related to laminar viscosity mu del u del y, and that is equal to constant. And again from the definition of the friction velocity v star, we can write tau w is rho v star square is equal to rho v star square, from which we can write that by integrating, let us write mu du bar dy is rho v star square. Then by integrating this, taking mu constant, v star constant, rho constant, we can write u bar by v star, if you take, is equal to v star by mu by rho is nu, v star by nu into y plus c, v star by nu into y plus c. Now this is a non-dimensional velocity u plus. Now this is a non-dimensional y coordinate, because nu by v star is a length dimension. Therefore v star y by nu is a non-dimensional. So y by nu by v star is non-dimensional. These typical non-dimensional quantities are defined in turbulent flow, y plus plus c. For the no slip condition at y plus is equal to 0, that means at y is equal to 0, u is equal to 0 means u plus 0, so that c is 0. So therefore we get u plus is equal to y plus. So therefore we get u plus is equal to y plus. So this is the law for the laminar velocity profile in the laminar sublayer, and this is the equation for the velocity profile of the turbulent flow in the turbulent zone near the solid wall. So from the experiments we can find out the values of this constant to adjust with this ln term, because this is dimensionless, and finally the results come, which was the contribution of the scientists known as Nikuretse, who also made a major contribution to it. Now, if you see, this is the thing. So, in the laminar sublayer, now it is plotted with y plus against u plus, u bar by v star, that is nothing but u plus in a semi-log graph paper. Because this equation is such that in this side it is ln, this side there is no log, so therefore semi-log it will be showing a linear profile. So, this is u plus is equal to y plus, this is the laminar sublayer. So, laminar sublayer extends 0 less than y plus less than equal to 5 is the laminar sublayer, where the equation of velocity profile is u plus y plus. This is a curve because it is semi-log. This is the logarithm side, this is the normal graph. Then in the buffer zone, which is defined to be y, yes, which is defined to be 5 less than y plus less than 60 is the buffer zone. Buffer zone, the velocity profile is like this, 5.0 ln y plus minus 3 point. And in the fully turbulent zone, that means this u plus the same equation, buffer zone and fully turbulent zone with the change in the constant, this is 2.5 is the constant, 5.5. So, this will be less steep, and this follow this rule, u plus y plus in the fully turbulent zone, where y plus greater than 60, fully turbulent zone, fully y plus. So, therefore, this is the laminar sublayer velocity profile, u plus is equal to y plus. This is the buffer zone, this logarithmic law with change in the constants between in the buffer zone and fully turbulent zone, velocity become less steeper. This is physically because in the fully turbulent zone mixing is much more between the particles because of their high turbulence level, so that the velocity profile become more steep and less steep, sorry, and it is more steep. This is the total picture of the turbulent flow velocity profile near a solid wall, of course with zero pressure gradient. Today I stop it here, and this is the concluding lecture for your turbulent flow theory, introduction to turbulent flow. As such, turbulent flow is a very vast topic, and the turbulence modelings and more details of the turbulent flow is kept beyond the scope of this basic level fluid mechanics course. This will be taught in an advanced fluid mechanics course. We have seen earlier there are topics like incompressible viscous flows, there are topics like boundary layer theory. These are the advanced topics, so only introductory concept and a brief description of these topics have been given to your primary level or basic level fluid mechanics course. More detail of these advanced topics will be taught in a second course of fluid mechanics or an advanced course of fluid mechanics. Okay. So, with this I conclude this section, this chapter, and at the same time the entire course on fluid mechanics.